This is David Spears, Civil Engineering Instructor at Texas Tech University, talking about CE 3303 solids. We're talking about shear and moment diagrams by the equation method. This is really just statics, but this is a good example for showing how it gets complicated pretty fast. I've got a beam 10 meters long, concentrated couple, force couple moment, 80 kilonewton meters at the left end, which I've called A, which is a roller support. Mid-span, I have a concentrated load of 15 kilonewtons, and then I have a uniformly distributed load of 5 kilonewtons per meter, all the way to the end of the beam, which I've called point C. Mid-span is B. I solve for my reactions, and I've noted we've had a lot of problems with misunderstanding of how we treat this 80 kilonewton meter, a concentrated force couple, when we're solving for reactions. It already has length in it, meters, so it doesn't matter where it occurs, it's still 80 kilonewton meters. So my sum of moments equation, taking moments about point C, sum is 0, counterclockwise is positive, is equal to negative 80, because it's in the clockwise direction, plus 15 times 5, which is the moment arm. 15 is the force. My uniformly distributed load, I write the resultant as 5 times 5, or 25, and its moment arm is in the center of that distributed load, which is 2.5 meters out, so it's 5 times 5 times 2.5, minus my AY reaction times its moment arm of 10, minus, because it's going clockwise direction, which is opposite of my positive sign assumption. So I do the math. AY is equal to these numbers added up, divided by 10, 5.75 kilonewtons. So, just reviewing one more time, it doesn't matter where that 80 kilonewton meter moment is, it's still just 80. It doesn't matter if it's here, here in the midspan, or over here at this other end. It still acts on the beam. Now, I want to look at my sum of forces in the Y. It's pretty easy. I've just got my reaction that I just solved for, 5.75, up, positive, minus 15, minus 5 times 5 for the distributed load, plus CY, reaction at the right end, works out to be 34.75 kilonewtons. Now I've got my reactions, I'm ready to start writing equations. I've got two places where the load changes in the middle of the span, so I need to write two equations. One I've kind of drawn in blue. X1 is somewhere between points A and B, anywhere between points A and B actually. So I draw a free body diagram of that segment. Just put the loads that are acting on that segment. 5.75 reaction, 80 kilonewton meters, nothing else happening, so I just visualize that section's cut somewhere like there. Then I have my internal forces, my shear and my moment. I do sum of forces in the Y. That's real easy. It's just 5.75 minus V, so V is 5.75 constant. We'll graph that in a minute here. Doing sum of moments about this point where I've cut my section, which I call point 1, counterclockwise positive, it's equal to 0. I have minus 5.75 times this variable dimension x1, clockwise, so it's negative, minus 80, because this is a clockwise moment, my external force, moment couple, plus M, my internal moment reaction. So rearranging that equation, I just get that M at any point along there between A and B is 5.75x plus 80. I can evaluate it at its boundary conditions. At 0, plug in 0 for x and I get 80. The other end of the boundary of that first segment is at x equals 5. So plug that value 5 in there and I get my moment is 108.75 kilonewton meters. We'll graph that here in a second. First, let's go to segment 2, which is a distance x2 from the left end somewhere between B and C. I write all my forces on there, show my dimensions, even show the resultant of this distributed load, which I've cut in the middle, so it's not equal to 5 times 5 anymore. It's actually, value is 5, the kilonewton per meter force or amount, times the horizontal distance, which is from here at point B out to this point where I've cut my section, is x2 minus 5. So I've shown that in red here. So the value of that load is 5, the magnitude, times the horizontal distance, x2 minus 5. So it becomes a variable. And just looking ahead, it is located at half of that distance, x2 minus 5. So from this right end where I've cut my section, so that distance, moment arm, which I'm going to use here in a second for my moment equation, is x2 minus 5 divided by 2. It's the centroid of that rectangle of dimensions 5 by x2 minus 5. Okay, so first let's do sum of forces in the y direction. Positive is up, it's equal to 0. 5.75 is my reaction, minus my 15 kilonewton concentrated load, minus this value of this resultant of the distributed load, which I've said is 5 times quantity x2 minus 5. And then I have this internal force reaction, V2, which is negative because it's down. Rearrange, do all the math. I get V2 is equal to 5.75 minus 15 minus 5 times x2 plus 25. I'm just distributing that 5 over the quantity x2 minus 5. Combining my common terms, I get that V2 is equal to 15.75 minus 5x2. Evaluated its boundary conditions of 5 and 10. At 5 it's equal to negative 9.25. At 10 it's equal to negative 34.25. I just get that by plugging in 5 for this equation and 10 for this equation. And do the math. Okay, then my moment gets really fun. I'm going to sum moments about this section, this point where I've cut the section, point 2. Counterclockwise positive is equal to 0. Start off with at the left end, I've got negative 80 because it's clockwise, opposite my sign assumption of positive. Minus 5.75, it's also clockwise, times the distance, the moment arm, x2, plus 15, this is counterclockwise, so it's plus, times its moment arm of x2 minus 5 for the concentrated load, about this point. Now I get to the really fun part, my distributed load, which is the magnitude of it's 5 times x2 minus 5, this quantity right here. Its moment arm is, I say, half the distance, x2 minus 5. So now I'm going to get a quadratic, and the last moment I have is my internal moment m2. I do the math, expand out these equations, I get negative 80, do the math here, 15, distribute that over x2 minus 5, I get these two terms. Then I get 5x2 minus 25, multiply the 5 times those two terms, and times my moment arm, which is x2 minus 5 over 2, which I've expressed a little bit simpler here. I do that math. This part of it is equal to 2.5x squared minus 12.5x minus 12.5x plus 62 for the half. Combine all my common terms, pull it all together. My moment at any point in there, x2, distance from the left end, is negative 2.5x squared plus 15.75x, which is those terms underlined in red, plus 92.5. Evaluated its boundary conditions of 5 and 10. At 5 it's 108.75, which is nice because it matches up with my quantity from my X1 segment, 108.75, and then at 10 it goes to 0, which is nice because it's consistent with my support condition, which is a pin where I can't have a moment. So that's the answer. Now I just graph those points, segments 1 to 2, I mean A to B. The shear is constant, 5.75. Then, thinking about my graphical method of solution, my 15 kilonewton force down causes it to jump down 15 kilonewtons from 5.75 to negative 9.25, which is consistent with my shear from segment 2 at x equals 5, negative 9.25. Then it starts sloping down all the way to negative 34.25. So there's my shear diagram. Looking at my moment diagram, it starts off at 80, which is consistent with my external force, and it goes up in a straight line because it's a function of just x, so it's a straight line function, to 108.75 in the center of the span at x equals 5. Then I have to go to this equation, and it's an x squared equation. It's a second order term, and I've forgotten to write that on here. You need to write it on your moment diagrams. That's a 2-degree curve, and that's a 1-degree curve. Okay, so I'm starting off at 108.75. I'm curving down. You can see the slope is negative, and it goes down to 0. So looks like that, consistent with my graphical solution. That's what they look like. Okay, real quickly I want to digress or regress or make the point that if this load, it's pretty complicated because it's just a uniformly distributed load. If it was a triangular shaped load, we'll probably have some of those on homeworks and maybe even a test. Really gets complicated fast. Say I had this example, really simple loading. It's 10 meters long, kind of like this one, with a uniformly increasing distributed load starting in the middle. At the end, it's 3 kilonewtons per meter at its peak. So I've already solved for the reactions. 1.25 kilonewtons at this end, 6.25 kilonewtons at the right end. Remember that the resultant of this triangular shaped load is just the area, which is a triangle, 5 long at the base and 3 at the peak. 5 times 3 divided by 2, because it's a triangle, 7.5 kilonewtons is a resultant of that. Anyway, use that. And then its centroid, it is the centroid of that triangle, or where the resultant is applied, equivalent resultant, is 1/3 of the distance from the base, which is 5 meters. The base is 5, so it's 5/3 is the moment arm. I used all that to get these reactions. Okay, now on these triangular shaped loads, I need to write an equation. I need to know what the slope of that line is. Remember that my slope line equation is y is equal to mx plus b, where b is the y-intercept. In this case, my y-intercept is 0. So this works out to be m is equal to y over x. So y is 3, x is 5, so my slope is 0.6. I'd express that kind of like we express it sometimes in statics or elsewhere. It's 3 over 5 slope. It's going up 3 units for every 5 units it goes over. Okay, so let's say we're going to write a segment, one of these like segment 2, out here in the middle of the span, of the right half of the span, to the right side of the half point. It gets complicated real fast. My sum of forces in the y is equal to 0, is equal to my reaction, minus this force, which is the slope, 0.6, times the x distance. So I'm trying to find that point right there. The value at any distance x 2 from the left end, or x minus 2, x2 minus 5 from that point where the load starts. So that value is mx, which is 0.6, my slope, times my x value, which is x2 minus 5. So that's what this expression is right here, 0.6 times x2 minus 5. That's the value of that, the height of that triangle. The base of the triangle is x2 minus 5. And it's a triangle, so it's times 1/2. So the resultant force, I've kind of written it here in red also, is 1/2, because it's a triangle, 0.6 x2 minus 5. That's the height of that point right there, times x2 minus 5, which is the base. So I've already got a quadratic equation. Now I'm just in the shear. I do all the math, express it out. V is equal to negative 0.3x squared plus 3x minus 6.25. And I would have to evaluate that if I was graphing this at 5 and 10. And it's going to be a curve, a second order curve for a shear diagram. Okay, if you thought that was bad, let's look at the moment. Doing some moments at this point. Simple negative 1.25x, because it's clockwise. Then I take this quantity, which is the resultant that I've kind of put with the bracket under here. This is this resultant, 0.6 x2 minus 5 times x2 minus 5 times 1/2, because it's a triangle. Then its moment arm to this point here is the x2 minus 5 distance divided by 3, because it's a triangle, 1/3 from the distance from the base, plus m. So it took me a page to write all this out. I've simplified it and summarized it right here. My moment is equal to a negative 0.1x cubed, so I've got a third order curve, plus 1.5x squared minus 6.25x plus 12.5.